It's time to get started. Hi, everyone, and welcome to another ARENA seminar. I'm Panos Gastis. I'm the chair of the organizing committee of the online seminars this year. Currently, I'm a postdoc at Los Alamos National Lab, and my research is in the field of experimental nuclear physics. Today, we are very happy to have with us as a speaker, Dr. Samuel Giuliani. Samuel is currently a research fellow at the European Center for Theoretical Studies in Nuclear Physics, also known as ECT, and is in Trento, Italy. He received his PhD from TU Darmstadt in Germany back in 2017. And before moving his current position, he also worked as a postdoc at Michigan State University in the United States. He specializes in the field of theoretical nuclear physics, and among others, he has done extensive work on the study of nuclear fission properties and nuclear masses that can strongly affect our process nucleosynthesis in kilonova. Now, quick note as always, before we jump to the presentation, please keep your microphones muted during the talk so we keep the background noises low. And if you have any questions, feel free to unmute yourself and ask the speaker directly. Sam is going to receive questions during his talk. Or you can also use the chat, and you can type your question in the chat, and I'll transfer it to the speaker. So, Samuel, when you're ready, take it away.
Well, thanks, Panos, and also thanks to all the organizers for the kind invitation to give this talk. So, today I would like to show you some calculations regarding the estimation of the nuclear properties of heavy and super heavy nuclei and the impact of those for the air process nucleosynthesis. And I would like to start this talk actually with an image which probably is familiar to many of you, and that it summarizes the cosmic origin of the elements that we observe in the solar system. So what this figure is telling us is that with the exception of light elements up to boron, which are created either during the Big Bang nucleosynthesis or through the spiralations of heavier nuclei heated by cosmic rays, all the other elements are produced by different stellar nucleosynthesis process, like for instance, the fusion of lighter elements into heavier ones, which produce nuclei up to the iron peak. So this talk actually is focused on the heaviest part of this periodic table, which concerned the so-called air process nuclei. And actually, I should already start making a disclaimer that contrary to what this very nice figure suggests, whether neutron star mergers are the main astrophysical site responsible for the production of air process elements is still an open question in the community. And actually, let me show you one kind of challenge that neutron star merger face when they're compared with astronomical observation. So this plot here from Wehmeyer and collaborators show the evolution of europium with metallicities in our galaxy, in the Milky Way. The magenta crosses here represent observational data, while the red, green, and blue dots represents model abundances that are obtained when neutron star mergers are assumed to be the only contributors to the enrichment. So what these kind of studies are suggesting is that neutron star mergers face some problems to reproduce the large scatter of europium over iron, which is a typical europium, is a typical a characteristic nuclei that we can take for the air process that is observed, the scatter that is observed at low metallicities. Of course, different methods have been proposed in order to address these kind of issues, either by invoking additional astrophysical scenarios responsible for the production of air process elements, like for instance, collapsars or magnetorotational supernovae, or even within the neutron star merger itself. But regardless of what is your personal choice for addressing these type of issues, the message that I would like to bring is that understanding the cosmic origin of the air process elements requires actually a strong multidisciplinary effort, which involves not only astronomical observations, but also the modeling of the astrophysical site, possibly responsible for the production of air process elements, as well as the study of the chemical evolution of our galaxy, and of course, the nuclear physics powering the air process nucleosynthesis. That will be the main focus of this talk. So actually now I would like to show you one example of how nuclear physics uncertainties can impact other branches related with the study of air process elements. This here is a plot from Benoit Coté and collaborators, which show the binary neutron star merger density rate as a function of the redshift, which is a proxy for the look-back time. As a reference, actually, you can look at this purple band here, which represents the estimation of the local rate made by the LIGO-Virgo collaboration after the detection of the neutron star merger event GW170817. Now, this is a quite busy plot, so I ask you to focus in the blue bands and lines, which actually represent the estimation of the rates that are required in order to reproduce the amount of europium that is observed in the Milky Way. So the dashed lines here are the rates that are estimated when one assumes that each neutron star merger event ejects between 10 to minus 5 to 10 to minus 6 solar masses of europium. These are actually the boundaries that were obtained by looking at the electromagnetic counterpart produced by this neutron star merger event. Now, this darker blue blend here instead are the rates that one obtains when uncertainties in galactic chemical evolution models are taken into account. And now, if you look at this very large light blue band, which spans over 2 orders of magnitudes, this actually represents the estimated rates that are obtained when europium yields are obtained from nuclear reaction network calculations, and therefore accounting for nuclear uncertainties. So actually, what we see here is that this very large variation in the estimation of the uncertainties produced by the nuclear uncertainties strongly reduce our ability to understand what is the role of neutron star merger in driving the chemical evolution of air process elements from first principles. It is therefore important to somehow proceed further and trying to reduce this kind of uncertainties. In order to do that, let's just try to see what are the main mechanisms responsible for the R process and how nuclear physics enters on it. So as you probably all know, the R process occurs in astrophysical scenarios where the timescales for the neutron capture are much shorter than the timescales for the beta decay. This actually allows the material or the seed nuclei that are present in the environment to capture several neutrons before beta decay, moving the material far from stability and closer to the neutron-rich line. An important characteristic is obtained when this air process path encounters a neutron shell closure, because the extra stability of this nuclei respect to the neutron capture allow the material to suffer multiple beta decays, therefore bringing the air process path closer to stability, where lifetimes are longer. And of course, these longer lifetimes produce an accumulation of material that result in the typical peak structure that we can observe nowadays in the air process abundances. So if we ask ourselves how far can this air process proceed, this question can be answered by the number of free neutrons that the seed nuclei can capture. And therefore, in the case of neutron to seed ratio that are of the order of several hundred or even thousands, like those that we found in neutron star mergers, what we will have is that the air process path will cross the whole nuclear chart, reaching the region where nuclei become unstable against fission and they split in lighter fragments. Then after the first second, neutron capture will exhaust and beta decay will start to dominate. And then the material will start to decay towards the valley of stability, leaving behind, for instance, the air process pattern that we discussed before, where the different peaks just testify the presence of the neutron shell closures are neutron number equal 82 and 126. So if we now look at the location of the air process path, which in this picture is depicted with this light gray line, we can already understand what is the problem related with nuclear uncertainties if we compare it with the region where experimental data is available, that are these red squares here. Basically, what this very schematic picture is telling us is that in order to simulate the process nucleosynthesis, we have to model the nuclear properties of thousands of nuclei for which experimental data is not available. And therefore, this introduces large uncertainties that then propagates in network simulations and can affect the final outcome, as we have seen in the case of the COTE study. Of course, improvements from these sides are coming from two different sources. One requires better modeling of the nuclear properties of these very exotic nuclei, and the other improvements are coming from the next generation of experimental facilities, like for instance EFRI, but at MSU and for GSI, that will enlarge the region of experimental data that could be of interest for the air process simulation. Another important feature that we can just extract from this very schematic view of the air process is that in order to achieve such short timescales for the neutron capture, we need an astrophysical site with high neutron fluxes, which actually is telling us that the astrophysical site hosting the Earth process must be a transient object. And actually a very good candidate for such situation are, of course, neutron star mergers. So this video here shows that two neutron stars gravitationally bound that orbiting each other and that start to spiral in closer and closer by losing energy via the emission of gravitational waves. Then, of course, they collide, emitting a gamma ray burst and eventually other electromagnetic counterpart. One important thing to keep in mind about this kind of event is that they have a large variety of ejection channels. And what one means with this is that the composition of the ejecta changes a lot in the different stages, and actually also strongly depend in the kind of central object that is formed after the merger. So during this talk, I will mostly focus on results obtained with trajectory simulating the dynamical ejecta, that is the ejecta that is produced at the initial stages of the merger and that is particularly neutron-rich. However, something that we have always to keep in mind is that the impact of nuclear uncertainties, of course, are going to be also affected by the composition of the ejecta that one is looking at. So, another important characteristic of the air process nucleosynthesis occurring in neutron star merger is that these events produce a large amount of radioactive nuclei, which decay emits a lot of energy that eventually can trigger an electromagnetic transient. Actually, studies from roughly 10 years ago show that the peak luminosity of such electromagnetic transient will be of the order of 1,000 times brighter than a nova, and therefore they call it kilonova. So this plot here actually show the predicted luminosity of these kilonova as a function of time, where one can see that in the time scales between 1 and 10 days, the dependence closely follows a power law, which actually is an indication that the heating rate is dominated by by the radioactive decay of a broad distribution of nuclei. So the important message actually that one can extract from these studies is that both the shape and the magnitude of this kilonova light curve strongly depends in the composition of the ejecta. And this is because not only this determines the amount of energy that is emitted, but also its thermalization and the opacity of the environment. Therefore, a direct detection of this kilonova light curve will provide a direct confirmation that actually neutron star mergers are an astrophysical site hosting their process. And as you probably all know, this is exactly what happened on August of 2017, when firstly the gravitational wave signal of neutron star mergers was detected by the LIGO-Virgo collaboration. And roughly 11 hours after this event, telescopes around the world detected the kilonova light curve in the Hydra constellation. So this inset here, actually what is showing is just an image of the kilonova light curve that was observed around 11 hours afterwards, and how nothing was there 20 days before the merger event. So when people compare actually this astronomical observation with the model predictions, they found a very good agreement between both, which actually gave a boost of confidence regarding the validity of the understanding of this process. Also, it was clear from the beginning that since several studies predicted that at late times the heating rate will be dominated by few nuclei, it was clear from the beginning that there was the possibility to try to understand if some particular nuclei could leave some detectable fingerprints in this kilonova light curve. And actually in 2019, Watson and collaborator found traces of strontium in the kilonova spectrum, which provide the first direct identification of an element from the kilonova light curve. But if we focus now on heavier elements, what several recent studies suggested is that fissioning nuclei as well as translate alpha emitters could strongly impact the kilonova light curves at timescales of several weeks. So this is shown as an example in this plot from Meng-Ru and collaborators, where the observed luminosity and predicted ejecta heating rate are depicted as a function of time. So the symbols here represent observations, while the lines are different calculations. So these red dashed lines represent, let's say, the standard calculation that was obtained from the nuclear network simulation, while the green thick line represent the results obtained when a relatively small amount of californium-254 is introduced. And actually one can see that the spontaneous fission of this element, which has an half-life of roughly 60 days, can strongly impact in producing a characteristic bump in the light curve of the kilonova. Unfortunately, the astronomical observation didn't have enough accuracy in order to discriminate between this scenario, since the open symbols here that we observe only represent the lower limit. But it's clear that future kilonova observation, and hopefully more accurate one, could help us to understand what is really the composition, or actually if traces of fissioning nuclei or alpha of translate alpha emitters could be identified in the kilonova light curve. So the rest of the talk actually will be focusing what is the impact of fission in the kilonova light curves, and how somehow microscopic calculation will help us to understand what are the possible scenarios regarding the production of translate nuclei in their process nucleosynthesis. So the fact that fission plays a crucial role during the process nucleosynthesis is something that has been argued since a long time. And particularly in the latest years, there have been a plethora of studies where trying to better understand and pin down what were the consequences of fission in terms of abundances and kilonova light curve. The archetypical example is this plot from Marius Eichler and collaborators from 2015 showing the abundances as a function of the mass number. So the black dots here represent the solar abundances, while the lines are the model predictions obtained using different fission fragment distributions. And one can clearly see that fission fragments actually can change the abundances above the second peak in a quite drastic way. Now, the problem of addressing what is the impact of fission for their process is that the number of fission datasets that are available are quite reduced. And for some observables, like for instance, fission fragment distributions, most of the data that is available are either parameterization or extremely phenomenological, which means that the validity, far from stability, is highly debated. So the long-term goal that we're pursuing with actually a lot of people in the community are pursuing is to compute a larger set of reaction rates and fission properties obtained from microscopic calculations, which eventually could provide a consistent set that can be used for our process nucleosynthesis. So actually, let me now give a very brief explanation of what I mean by microscopic calculation in the context of fission. And I apologize for the few equations, but just bear with me for one slide. So the formula is that we are using for computing the fission and ground state properties of transient nuclei is the Hartree-Fock-Bogleubov formulas, where actually the many body wave function is described as a quasi-particle vacuum, which is obtained by minimizing the total energy. Now, in order to compute the fission properties, we have to study what is the evolution of the energy as a function of the different deformation describing the fission path, which actually forms a so-called energy landscape. And this is obtained just by introducing some Lagrange multipliers which constrain the nucleus to the proper deformations. Now, the final ingredient in order to perform our nuclear structure calculations is a phenomenological ansatz for the effective nuclear-nuclear interaction, which is given by an energy density function. In the market, you can find a huge variety of functionals, and during this talk, I will mainly focus in the results that we obtained using this particular one called BCPM. But I will also later show some results related with the Skirm and the Gogny interaction. So the structure that we follow in order to propagate our uncertainties from nuclear structure to the network calculations is to start computing the fission properties and binding energy using the energy density functional, and then to convert them in reaction rates using the Hauser-Feshbach statistical theory. Then these reaction rates can be plugged in a nuclear network simulation where we study the air process abundances and the kilonova light curves. So let me show you actually the results that we obtained in our calculation and the comparison with other models that have been extensively used for air process simulation. So this plot here on the left show the fission barrier height as a function of the neutron and the proton number. So for those of you that are not familiar with fission, the fission barrier height is just telling you a proxy regarding the stability of the nucleus against fission. So of course, the higher is the fission barrier height, the more stable are the nuclei against fission. And the plot here shows the comparison of our calculations in the lower panel with HFB14 and FRDM plus Thomas Fermi barrier. The red lines that you see here represent nuclei that are predicted to have a neutron separation energy of 2 MeVs, which roughly describe what is the location of their process path. So what we can see from this plot is that there are some common characteristics among these different models, like for instance, an enhancement of the barrier around the neutron number 184. And also all the models show a region of vanishing fission barrier where nuclei are expected to be extremely unstable against fission. And actually, the critical region one can already observe from this plot occurs here around the neutron number 184, where the fission path has to cross this region as very low fission barrier. So we can expect that some of these models will allow their process path to proceed towards higher mass number, while others actually will terminate their process here. And that is exactly what we see in our network calculations. So this plot here on the right show the air process abundances that are obtained at the so-called freeze out. That is the moment when the neutron to seed ratio equals 1. And the abundances are depicted as a function of the neutron and the proton number for the different models, and exactly as a function, and this is in logarithmic scale. And actually what we can see, for instance, for FRDM plus Thomas Fermi barrier, that is the model predicting the lowest fission barrier, is that their process terminates here at neutron shell closure 184, where nuclei are split to lighter fragments and depopulate the lower region of the nuclear chart. Conversely, HFB14, the larger barriers predicted in this region allow the air process path to overcome this neutron shell closure and just proceed towards heavier nuclei. While in our calculation, the situation is somehow in between, where we can see a quite large accumulation of material, but then their process cannot really proceed much further. This, of course, has a strong impact in the final abundances, as it is shown here on this left plot, where the abundances are depicted as a function of the mass number, and these are obtained now at 1 gigayear. So we see that actually the models predicting a larger accumulation of material around the neutron shell closure 184 end up with an accumulation of final air process abundances above the second peak, as actually was, as we have seen already in the plot of Eichler and collaborators. And also another consequence is that this large amount of nuclei release of fissioning nuclei, release a lot of neutrons that are captured at later stages of the air process, shifting the peak that you see here towards larger mass numbers, which is also a phenomenon that was described in the paper of Marius Eichler. So of course, something that I mentioned before and that I want to recall now is that this kind of impact that we see strongly depend in the trajectory and the astrophysical and the thermodynamic condition of our trajectory. So for instance, we repeat the same calculations, but looking at a trajectory that mimics the viscous outflows from post-merger accretion disk, which actually are trajectory which are less neutron-rich. And what we found, of course, is that the accumulation of fissioning nuclei around the neutron shell closure 184 is smaller also for HFB and BCPM. And this is because when the air process path reach this region, most of the free neutrons are already exhausted. As a consequence, the abundances predicted by the models are similar to those that we have seen in the dynamical ejecta, and therefore the impact of the different fission rates is smaller on the final abundances. As a next step, actually, we look at what was the impact of our our calculation on the kilonova light curve. And the answer is that actually what we found is that the propagation of the different fission rates and fission barriers acts in a non-trivial way with respect to the evolution of the ejecta heating rate, which are plotted here as a function of time for the three different models that we were seeing before. For instance, if we look at FRDM plus the Thomas Fermi barrier, what we see is that due to the very low fission barriers predicted by this model, there is no bump associated with the decay of the 254 Californium. And this is because the progenitor of these nucleus are destroyed by fission. Conversely, HFB14, which had larger fission barriers, allows to accumulate a quite large amount of 254 Californium, and therefore show this characteristic bump that was already discussed by Zhonglin Zhu, Meng Wu, and others before. Finally, in the case of BCPM, even though this model predicts fission barriers which are similar to HFB14, we don't see any accumulation of 254 Californium. And this is because the large amount of fissioning nuclei that are accumulated during with this model at the freeze out actually emits a lot of neutrons, which then destroy the progenitors of 254 Californium by late neutron-induced fission. You can think about this process in a similar way like those happening in nuclear reactors in power plants, where fissile nuclei, which just are destroyed by neutron capture, then emits neutrons, which at the same time produce other or induce other fission properties in a self-sustained chain. So besides the technical details regarding the variation of the kilonova light curves, something that seems pretty exciting is the fact that several studies suggest that the kilonova light curves are very sensitive to the nuclear properties at neutron number 184, which actually means that eventually with further studies, one could try to understand which kind of physics can be extracted from the kilonova that could give us access to information about the nuclear properties in a region of the nuclear chart, which probably will not be accessible in future experimental facilities. So, of course, other studies also have been looking at the impact of the variation of nuclear models in the kilonova light curve. And just for mentioning one of the latest one, this is a plot from Zhonglin Zhu and collaborators, where they look at the effective heating rate as a function of time when different models are used. So these results here correspond for a relatively neutron-rich trajectory, where a lot of fissioning nuclei are created. And this actually produces a large spread in the effective heating rate, because the population of those fissioning nuclei strongly vary, among these different models. So I would like now to make a very a small shift in the discussion and just show you a little bit some results related with the fission fragment distribution. So as we were seeing in the plot of Eichler and collaborators, we see that fission fragment distribution can highly impact the air process abundances. Another example is given by this work of Nicole Vacha and collaborators, where what they did was to use a recent calculation of the fission fragment distributions obtained from the FRDM model, which predicts a very broad distribution of fission fragments for these neutron-rich nuclei. What Nicole and collaborators found is that when you plug in these fission fragments distributions into network calculations, you have a much larger population of lighter nuclei, like for instance, silver and palladium, respect to just assuming a 50-50 split in the fission fragment distribution, which actually can have also some strong consequence in terms of observational data. Therefore, this of course is raising the question, or is again underlying the importance of having calculation of fission fragment distributions, which are possibly as consistent as possible with the calculation that we obtained for the fission rates, which actually means that we have to use the energy density function in order to compute our fission fragment distribution, and then combine those with the calculation of the reaction rates. In terms of formulation, what it means is that we have to switch from the probability of the nucleus to tunnel under the fission barrier, which is just the evolution of the energy as we stretch the nucleus. And actually, this is what represents the probability of fission and therefore the fission rates. We have to extend this formalism in order to understand which kind of fragments or which final products are produced during fission, and therefore construct our fission fragment distributions. Of course, in order to do that, one has to introduce some extension in your formalism, which, for instance, could be the Langevin stochastic calculation. However, in the case of energy density function, this is a very expensive calculations. And therefore, together with Giuliani, we introduced a novel method for the calculation of the fission fragment distributions, which eventually will allow the usage of microscopic input given by the energy density functional, but keep the computational cost reduced in order to make it applicable to the whole region of air process nuclei. So, yeah, I apologize again for just the few questions. Bear with me for just this slide. In a very simple scheme, what we do is to extract the information about the final fragments from smaller configuration and therefore from smaller deformations. And then we construct a microcanonical probability in order to understand what will be the final fragments that are populated. And this probability at the end is used in order to construct and to obtain our fission fragment distribution. And actually, an example of the results that we obtain is given in this plot, where we compare our calculation, that is this light blue band, with the results, with the prediction given by the scission point model of Lemaitre and collaborators, and the Brownian-shaped model of Manpower and collaborators that we were seeing before. Here, the experimental data is given by the different symbols. So in general, what we found is that our models give us a quite good agreement with experimental data, even though there are some regions of larger deviations that are related with asymmetries in the yields. And when we compare our calculations with other models, like for instance, the one from Lemaitre, we found that for more neutron-rich nuclei, our calculation seems to be in better agreement with experimental data. And conversely, when we compare it with the recent calculation of Matthew Manpower and collaborators, we see that actually the large broad distribution that they found in their simulation is actually not in agreement with experimental data, and actually also not with our calculations. Therefore, the next step is to extend this estimation to the whole nuclear chart, of course, of relevant for the fissioning air process nuclei, and then try to study what is the impact of such nuclear input for both their process abundances and the kilonova light curve. Honestly, okay, in the last minutes, what I'm gonna discuss is just very quickly how we plan in the next future to better assess what are the uncertainties related with nuclear physics for their process nucleosynthesis. And actually the idea is that the example that I gave you before about the effective heating rate is just one example of how nuclear models show large discrepancy far from stability when we talk about energy density functions. So the idea is to combine our nuclear models with Bayesian analysis in order to improve our calculation and give an estimation of the uncertainty related with our calculation. This actually can be done in a very simple way, just by modeling the discrepancy between the theoretical calculations and experimental data, and then try to construct some emulators of these discrepancies. In our case, these emulators are obtained from Gaussian processes, and then you can use those in order to correct for some systematic uncertainties your theoretical predictions, but also you can use those in order to assess uncertainties just by taking the root mean square, the standard deviation from the posterior distribution given by your Monte Carlo sampling. So one example of the impact of these calculations is given by this table, where what we are showing are the 1 proton and 2 proton separation energy that we obtained when different models, and actually the results that we obtain when we correct these models with our Bayesian approach. So usually we see that we can have these Gaussian processes can reduce the root mean square deviations up to a 40%. But of course, the impact is not always homogeneous. So some models seems to be more affected than others, and basically is related with the way how they were fitted to the experimental data. Of course, this can also be used by, as I mentioned before, just to provide uncertainty bands in order to understand what are the variations of your raw predictions, but also is it possible to mix the model posteriors in order to perform what is called the Bayesian model averaging, where actually one try to maximize the wisdom of the different models combined in one single prediction, which usually performs as good as the best as the best models. So this actually was the last result that I want to show you, and we just quickly summarize the talk. I hope I convince you that the observation of the kilonova light curve associated with the neutron star merger event GW170817 push their process studies in a very exciting area, and that better nuclear structure calculations are required in order to extract the maximum information regarding kilonova light curves. Also, I hope I convince you that energy density function can be an extremely valuable tool for performing air process nucleosynthesis studies, since they can be combined with Hausser-Feshbach calculation for obtaining stellar reaction rates, and then one can be used in order to extract the fission yields with Langevin or similar approaches. And finally, they can be combined with Bayesian analysis for quantified nuclear input. Then we have seen how their process is extremely sensitive, or can be extremely sensitive in some particular condition, to the fission properties at n equal 84, and that therefore more studies are required and more nuclear input are required in order to better understand the possible consequence of this physics. And regarding the future, we are working together with the people at MSU to perform a systematic calculation of the fission fragment distributions that eventually will help us to better understand what is the impact of fission in the final abundances of producing during the arc process, and also eventually to understand the possible connection between the co-production of nuclei in the different regions of the nuclear chart. Of course, one necessary step will be to increase the amount of studies related with energy density function in order to better explore our systematic uncertainties in our calculation. And from this point of view, surely Bayesian machine learning techniques will be very helpful in order to provide quantified nuclear inputs. With this last slide, actually, I would just like to thank all my collaborators, particularly the PhD students which are within here involved, and of course the fundings for this project, and all of you for your attention. Thank you so much.
Thank you very much, Samuel, for the very nice presentation. Are there any questions for the speaker from the audience? You can unmute yourself, or you can type your question in the chat.
Friedel Thielemann, is okay?
Yes.
Hi, Friedel, yes.
First of all, congratulations for your very nice talk and results. Just a dumb question. You had one plot where you compared fission fragment distribution results, and one was the FR, the finite range liquid drop, and the other had a line, a blue line, which said 50-50. What was the meaning of 50-50? Is it symmetric fission, or what was the meaning?
Yeah, it's a symmetric split. 50? Yeah, exactly. Where you assume that actually all the nuclei split on a symmetric fission.
Okay, okay. That's what I assumed.
Correctly remember it. Yeah, I hope I'm not saying it wrongly, but yeah, you're assuming that actually all the nuclei split on a symmetric way. Okay.
Thank you.
There is a question in the chat. It says your fission barrier calculations are temperature dependent. What temperature scales do you expect during neutron star mergers? And how did those temperatures affect your barrier calculations?
Okay, so the fission barrier calculations are not temperature dependent. Those are all computed at the so-called zero temperature. One could try to improve the calculation by taking into account finite temperature effects. However, for the case of tidal ejecta, we expect the material to be relatively cold. What I mean by that is that we are of the order of 1 gigakelvin. If you think in terms of neutron-induced process, that means that you are accounting for neutrons that have a thermal energy of 60 keVs, which actually is not very high, and therefore we assume, or we can expect, that the zero temperature approximation is a quite good one for the calculation of the fission rates. But yes, surely that depends. Once again, that depends a little bit also in the ejecta that one is looking for. So the contact interface could be heated to higher temperature, and sure that one could try to improve a little bit the calculation. However, doing finite temperature calculation is probably right now is a little bit too expensive from the computational point of view, and we expect the impact to be quite minor.
Are there any other questions?
Hi, Samuel. If I may, congratulations, very nice talk. I would like to ask you about the fission of old nuclei. As you certainly know, this is an even more difficult problem, and I don't think there is any single odd nucleus in your calculation yet. Were there any attempts to include odd nuclei in the network of leading to the abundance pattern in this very heavy range of nuclei, and whether people were trying to model those fission lifetimes and properties in any way?
Well, thank you, Jacek. That is a very nice question. So actually, yeah, we have to include odd nuclei, because without those we cannot perform the network calculation, which means that we have to, well, in our case, we took some quite drastic approximation for the odd nuclei. What we use is what is called the perturbative quasi-particle approximation. So we compute, instead of doing any kind of blocking that will increase the computational cost, we just perform regular mean field calculation with the constraint to the proper number of protons and neutrons. And then what we do is we add up the energy of the last quasi-particle. Of course, it's a very crude approximation, particularly for, well, for the binding energy, it works okay, it is what it is, but we know that for fission, that is surely is not enough. What should take into account way more complicated effects, from specialization energy to the effect in inertias and everything. And surely that is something that people have to look at, and something that we are working on, even just to improve the estimation of odd nuclei, even for just the binding energies and everything. Regarding fission, the point is that we have to remember that the nuclei that are relevant for their process nucleosynthesis are those, at least for the initial stages, which fission on very short time scales. This means that actually you are populating the nucleus very close to the fission barrier, what is the impact of inertias in that case is, honestly, I don't know, and it's something that surely is interesting to look. One may hope that eventually inertia don't play a too much important role, and that we can take some approximation that will allow to the estimation of a large range of nuclei. Yeah, sorry for the unnecessary long question. So the point is, the short answer is, yeah, sure, odd nuclei are extremely important, and there is a lot of work to do there.
Thank you, Samuel.
Other questions from the audience?
What are the most expensive parts of doing your calculations? Like, well, is there a particular piece of doing the DFT that?
Yeah. So when we say that it's expensive, the point is that depends a lot in the kind of observable that we want to compute. So let's say in the case, one example is that in the case of ground state energies, of course, the kind of deformations that you have to look, and therefore the self-consistent solution that you have to get is reduced to a few number of points. This at least for the case of even nuclei. While for fission, what you have to do, you have to model the evolution of the energy across a large range of deformations. Therefore, this means that usually you increase your computational time of, let's say, probably in principle, you can increase it by 1-2 order of magnitude if you cannot parallelize it in a smart way. So in terms of times, of course, once again, it depends a little bit in the kind of calculations that you want to do. You can expect that a single self-consistent calculation can just take from few seconds, okay, to a maximum of, let's say, 1 hour. So that is just 1 point. If you are considering, of course, depends a lot in the kind of symmetries that you want to break, and so on and so forth. Yeah, sorry, Jan, if I'm gonna give a more exact answer to that.
Oh, no, that was helpful. Thank you.
Other questions? I have one question, Samuel. So you mentioned when you talk about the heating rates in neutron star mergers, you mentioned californium 254, and some models show that it can be important, some others no. Have you identified any other nuclei that could, in principle, affect the heating rate there, apart from californium-254?
Yeah, so actually there have been a lot of people looking at that. So one of the first results regarding the impact of heating rates that have been, let's say, these probably are the regarding the single nuclei, probably the paper from Zhongli, Sinjavanayo, and Mengru Wu are those that describe more the impact of individual nuclei. So there are translated alpha emitters actually in the chain of radon and radium that are speculated that may play an important role, because of course the alpha particles thermalize in a more efficient way than what photons do. Therefore, they could play an important role also at these time scales of several weeks. These are actually probably the most promising candidates in terms of that. In this, so there is a nice collection from Mengru Wu, and also in this paper from Zhongli, Zhu, and collaborators. Also, they summarize the possible nuclei. The point is that, of course, it strongly depends in the alpha decays lifetimes and fission half-lives of those nuclei, which therefore the experimental data, we know what can work and what not. For the nuclei where there is no experimental data, the range of uncertainties is still very large. So we are still in the orders of magnitude, which is really too much in order to provide more precise estimations.
So you say that alpha emitters expect to play a more important role?
Yeah, exactly. So radon and radium change, I think, is I don't remember on top of my head, but I think it should be something around the 224 or something like that. Yes.
I see. And when you saw this this nice plot where you compare your theoretical fission mass distributions with the data, there were some cases with asymmetric distributions. Yes.
Yes.
About these asymmetries, like, was there any problem with the data, or this asymmetry is something that one expects to see?
Yeah, the problem is that these asymmetries, there are at least there are two possibilities. One is that, okay, let's say that it would be good to have better experimental data, because sometimes we found that there is some contradiction in the experimental results of this nuclei, and therefore it's a little bit difficult to assess the quality of your calculations where you cannot really compare with the data. The point is that some asymmetries actually seems to we could explain them by introducing some neutron evaporation method, which actually can account for the isospin asymmetry of this nuclei, which therefore can emit more or less neutrons, and therefore reproduce these some of the changes that we observe here in some fragments distributions.
Yeah, in this plot I see this California.
Yeah, here on that, would be.
Yeah, this californium-251 distribution on the right.
Yeah.
On the charts.
Okay, yeah, here cannot be, of course, neutron evaporation, because there is something on the fragment charge. Yeah, so actually, yeah, there are some. That is one of the regions where we have to try to understand what is happening and whether actually something that can be explained by improving the model.
Thank you. Any more questions for Samuel?
A short one. Just a couple of minutes ago, you showed a plot when you were talking about californium-254, a comparison with observations. There were some triangles at the end.
Yes.
Yes,
those are
on the right there.
Those are lower limits.
Observations tell us that californium is not so important.
Yeah, the problem is that those are lower limits. Therefore, since its lower limit is not really, I mean, it would be good if there would be more precise data, but yeah, actually it's not enough to distinguish. Yeah.
But it's not upper limit.
Yeah.
Okay.
No, unfortunately it's lower. Yeah.
Okay. Thank you.
Other questions? Well, if not, then once again, Samuel, thank you so much for your very nice presentation.
Thank you
And
all
for
for
accepting the
attending.
invitation. And I hope to see everyone in 2 weeks from now in our next seminar. And have a nice day. Bye bye, everyone.